Hi, today I'll be explaining how to solve the ordinary least squares problem using linear algebra. Let's start by defining the problem. We have a matrix A of dimensions m cross n whose numerical value is known. A vector of coefficients, w, is the variable in this problem. B is a vector of targets whose numerical value is also known. They're also called labels in a machine learning context. We want to select a weight vector such that the norm of AW minus B is minimized. In order to set the foundation, let us first understand a term in linear algebra called column spaces. What is a column space? Let's assume you have the following matrix. Now if I consider the columns of these as vectors, any linear combination of these vectors is said to be in the column space of A. Let's take a vector B equal to 196. This vector can be obtained if we set x1 to 1 and x2 to 1. So 196 belongs to the column space of A. If the last element was changed to 7, the vector cannot be obtained using any value of x1 and x2. So we say that it is not in the column space of A. Let's consider the vector 1, 5, 2. I can set x1 to 1 and x2 to 0 to obtain it, which means that this vector is in the column space of A. Similarly, for vector 0, 4, 4, I can set x1 to 0 and x2 to 1 to obtain it. This shows that all columns of A are in the column space of A. It's important to note that this expression is nothing but a matrix multiplication. If we name the x1, x2 vector as w, then any linear combination of the columns of A is just AW. This implies that for any vector w, AW is in the column space of A. If B is in the column space of A, then for some w, AW would be equal to B, and the objective function would be 0. For the purposes of this presentation, let's assume that B is not in the column space of A. Imagine the space to be three-dimensional, projected on a 2D surface. We have a vector B. The column space of A is represented as a plane shown here as a blue line. In order to envision the plane in 3D, think of the line protruding out from the screen as a plane perpendicular to the screen. If I take a random weight vector w, the point AW can be seen. The vector E can be defined as B minus AW, which is drawn. So effectively, the problem can be reformulated to state, how can I decrease the norm of this vector E by varying the vector w? It is clear from this diagram that the minimum norm of E will be achieved only when E is perpendicular to the column space of A. In other words, E is equal to B minus AW should be perpendicular to every vector in the column space of A. So, if the columns of A are denoted as A1, A2, and so on up to AN, then since all vectors from A1 to AN are in the column space of A, E should be perpendicular to all of them. This can be written as A1 transpose E equal to 0, A2 transpose E equal to 0, and so on and so forth. This can effectively be written as the matrix A transpose E equal to 0. Since A transpose E is equal to 0, we can substitute E equal to B minus AW in the equation. Rearranging the terms, we get A transpose AW equal to A transpose B. This equation in statistics is also known as the normal equation. This can be further simplified to say that W is equal to A transpose A, the whole inverse, A transpose B. This is the closed form solution to the ordinary least squares method. It's important to note that linear regression makes three key assumptions. The first is that the expected value of y for any given x is a linear function of x. The second is that errors are uncorrelated random variables with zero mean and constant variance sigma square. The third one is that the feature variables are independent. If the feature variables are dependent on each other, then the matrix A transpose A is singular and its inverse does not exist. In such a case, the closed form solution won't exist. The proof of this statement is beyond the scope of this video. Thanks for watching. If you like this kind of content, please like the video and leave a comment about what you liked or what I could have done better.